vacuum energy, still leaves a very important unsolved question for which we're very much in the dark about. As I said, the quantum vacuum is far from empty, so a non-zero value is no problem. Quantum fluctuations in the vacuum make it a very complicated state. And those quantum fluctuations can be positive or negative in their energy contributions. In a quantum field theory, if you try to calculate the energy density, you find that in the context of these theories that we call quantum field theories, you actually get an infinite vacuum energy. And the infinity comes about in a way that's not so difficult to see, at least. Suppose we try to calculate the vacuum energy inside of a box. If we try to calculate it over all of space, there's an extra infinity associated with the fact that all of space might be infinite. So let's eliminate that problem by just considering the vacuum inside of a finite-sized box that we can imagine. It's right here in my hands. And say we're just talking about the contribution from the electric and magnetic fields. The way that calculation is done is to imagine describing the electric and magnetic fields and their fluctuations inside this box by describing it in terms of what physicists call normal modes, which are just standing waves with patterns that are half a wavelength across, 1 wavelength across, 1.5 wavelengths across, and so on. And it's a famous mathematical theorem that the most general possible configuration of the field can be described as a sum of things like that, waves which each have a definite wavelength. And each wavelength, each normal mode, gives a contribution. The contribution is just 1/2 times Planck's constant times the frequency of that mode. It's half the energy that one photon of that mode would have. And the infinity comes about for the obvious reason, once you set it up this way, that there is no shortest wavelength. Whatever number of wavelengths you've added up, you can always find shorter wavelengths that will continue to add. And nothing stops that sum, so it diverges and gives you an infinite answer. Although in some cases, for some kinds of particles, it's positive infinity, and for other kinds of particles, it's negative infinity. But it's never a finite number. So OK, what does that mean about what's really going on? The usual assumption that physicists make is that the reason we're getting this infinity is that these theories called quantum field theories probably can't be trusted down to arbitrarily short distances. At some point, as you're thinking about shorter and shorter wavelengths, things probably just go wrong. And the real world is not going to behave the same way as our theory does, because our theory is giving this ridiculous answer that the energy is infinite. So the next best thing you can try to give some estimate of what the right answer might be, at least as a rough estimate, would be to cut this sum off at what you think is the shortest wavelength that you understand. You could say down to some wavelength, I think I know what I'm doing. I'll count all those energy contributions. And for shorter wavelengths, I don't know what happens, so I'll just leave that out of my calculation. To implement that, you have to decide what you think is the shortest wavelength that you understand. And that, of course, is something nobody really knows for sure. A number that seems very plausible to put into the calculation at this point is the energy scale at which we think quantum gravity becomes an essential element, because we're pretty sure that we do not understand quantum gravity. But we think we probably do understand, at least qualitatively, how things behave short of quantum gravity. So the scale of quantum gravity is what's called the Planck scale. And in terms of an energy, it corresponds to a colossally big energy by particle physics standards, 10 to the 19 GeV. So you could put this into your calculation as your cutoff and ask, what number do I get for the vacuum energy? Is it close to what we seem to be observing from the acceleration of the universe? And the answer is that it's a failure. And it's too large by a modest 120 orders of magnitude, which seems to clearly indicate that we don't have the foggiest idea what's going on here. So this is this gigantic theoretical failure that I talked about in my preview. We really do not understand or come close to understanding what it is that determines the energy density of the vacuum. Any theoretical estimate that we know how to make gives numbers that are vastly larger. You can find words to use to make this smaller than 120 orders of magnitude, but you can't get anywhere near the right number. Nobody knows how to. So that's the problem. And what I want to discuss for the rest of the time tonight is a possible way out of this problem that's provided by inflation in the multiverse. So I want to explain how that works. So first of all, I need to explain a little bit more about how we get a multiverse in the first place. Why is it that inflation is claimed not to produce just one universe, but in fact to produce an infinite number of universes for the price of one? I told you that inflation ends because this repulsive gravity material that drives inflation is unstable, was the word I used last time. Here it says metastable. It basically means the same thing. And what that means is that in any one location, if you were to sit during the inflationary period at one location and watch what happens around you, the probability that you would remain in an inflating region would decrease with time exponentially. That means it would be a half-life for you to remain in the inflating region. And after one half-life, the probability is a half, then a quarter, then an eighth, and it would tend towards zero. Inflation in any one place is overwhelmingly likely to end in some period of time. But the catch is that while all this is happening, the universe as a whole that's still in the inflating region will continue to inflate, which means exponentially expand. And this exponential expansion is, in fact, vastly faster in our theoretical models than the exponential decay. The consequence of that is that even though the repulsive gravitational material is decaying, its volume is actually increasing. The way that works, let me just clarify, is that if you wait for one half-life of the decay, half of it will have gone into normal material, will become no longer gravitationally repulsive. But the half that remains gravitationally repulsive, because of the exponential expansion, it now occupies a much larger volume than it did at the beginning when you started to wait for the half-life. So you have more inflating material at the end than you had at the beginning. And if you wait another half-life, again, it just increases in volume. And theoretically, this seems to just go on forever with no end that we can see. So the inflation becomes eternal. Once it starts, it never stops. The inflating region never disappears, but instead pieces of it undergo decay and produce these regions which are no longer exponentially expanding. And those are called pocket universes. We would be living in one of those pocket universes. And instead of one universe, we ended up with an infinite number of these pocket universes. And that collection of an infinite number of pocket universes is what we call the multiverse. And at least within our theoretical models, there's just nothing to stop this. In at least almost all versions of inflation, this just goes on forever. Now, in my introduction, I didn't mention a hobby of Andrew Chamblin's, but he liked to collect photographs of road signs with interesting things written on them. And this multiverse hypothesis is clearly exactly what that sign is about. So we have direct empirical evidence from a Texas road sign that eternal inflation really does happen. This road has no end. Okay, now how does that help us